Go ahead.
All right. Hi, I'm Tim Livengood with University of Maryland here at beautiful Goddard Space Flight Center. I'm going to tell you about our project, the Submillimeter Solar Observation Lunar Volatiles Experiment, which is variously pronounced as SOLVE or SSOLVE, or one crazy person calls it SSOLVE, but we don't respect that. I'll start with the result in case I run out of time. The critical thing is that we are going to look for the amount of water vapor above the lunar surface. The really critical dividing line would be a total column abundance of about 3 times 10 to the 14 molecules per square centimeter in the integrated column. If the amount of vapor is greater than that, then we're in the tricky regime of an actual collisional atmosphere, albeit extremely tenuous. And if it's less than that, then we've verified that we're in the regime of a surface-bounded exosphere, as we've expected for many decades now. So that dividing line, we can do that to a signal to noise of 180 in 10 minutes of observations. So very early on in any deployment on the lunar surface, we will have that fundamental answer and then know what we're exploring for afterwards. We have several other estimates for how much water vapor there might be above the lunar surface based on a variety of sources of information. They all disagree with each other. So one way or another, we will be sending some people back to the drawing board, and other people will be in the regime of, now I know what I'm dealing with. Our method is to land on the surface, stare at the sun, and measure the amount of vapor between us and the sun using a heliostat to track the sun. This is actually an obsolete depiction of the heliostat we have in mind, where we have some modifications, but the basic idea is there. We'll be looking actually for just 3 volatiles with this experiment. We'll look for water, for HDO, from which if there's enough water and HDO, then we could measure the D to H ratio, and OH with a 2.5 terahertz receiver. So that's breaking some new ground with the terahertz receiver. This is all, of course, motivated by 10 years ago. I can do math in my head. 11 years ago, we had a surprising discovery of widespread, hydration on the moon. Not deep hydration, of course, not copious, but everywhere, it seemed. This is from the Deep Impact mission and its epoxy extended mission. The spectrum you see here is one that actually was not published in the original paper by Jessica Sunshine, showing an integrated spectrum of the moon, in which the hydration feature at 3 micron is nice and clear. We also had, at the same time and in the same issue of Science as the epoxy result came out, we had spectra from Chandrayaan-1 with the M-cubed instrument. This is a more recent analysis of those data, showing that they confirm that there's some time of day variation in the abundance of water. And in order to have a variation with time of day in the amount of actual material in the surface, then it would appear that it has to migrate across the surface, which is part of the reason why looking for water vapor over the surface is a compelling issue. And finally, it was hard to see on my screen actually. We have observations from the LAMP UV spectrometer on LRO. That also shows a variation with time of day of the amount of water that they detect in the surface, with an interesting feature that what they find is a fairly steady amount with a relatively narrow dip in the amount of hydration at around noon. Whereas with a different LRO instrument, the neutron instrument on LRO, LEND, we found a suppression in neutrons near the dawn terminator that was fading to a minimum amount of neutron suppression in the afternoon. Now, this is in terms of the neutron neutron count rate. Since that's upside down compared to the amount of water, I have just conveniently turned everything upside down for you. So where you see it sticking up now, that would suggest more water. The challenge is that this is a very surprisingly large amount of water if we interpret the neutron suppression directly. So again, we have several different avenues that suggest complicated things going on. The idea with SOLVE is to just settle the matter. We will directly measure the amount of water vapor that's over the surface, and we will know what regime we're dealing with, which tells us, do we understand or do we not understand some of our sources of data? The method that we will use for SOLVE is pretty straightforward. Like I said, we stare at the sun, and we'll measure the spectrum. So not just doing something like measuring the bottom of an absorption feature in a neighboring region, we will measure the whole spectrum in order to get the spectral line shape, in addition to simply giving us an unequivocal identification of any water, HDO, or OH that's in the field. It also gives us additional physics from things like the line width will tell us about the velocity dispersion of the molecules above us. Now, one of the biggest problems that we face in looking for water at the moon, as everyone knows, is how do you distinguish the water you brought with you from the water that was already there? So that is an essential part of our observing plan. We have a calibration plan where the heliostat will rotate, including the radome that protects it from dust, to look at an internal hot load so that we can measure the internal water vapor that is trapped within the instrument and distinguish that from any water vapor we see external to the instrument. And also we plan on being located at the edge of a lander deck so that we can look at the neighboring ground and use that as a warm back source or backlight, and again measure the water vapor atmosphere that is attached to the lander itself. The lander will certainly be outgassing on its own. We will have recently been firing a rocket at the lunar surface that will have exhaust materials that are still coming out of the ground. So there certainly will be a local atmosphere created by our landing. We want to be able to distinguish that from anything we see looking at the sun. Our approach is pretty straightforward, and this fine PowerPoint generated artwork. We will just sit on the surface, stare at the sun, and watch the amount of water vapor change with time of day. If it's a surface-bounded exosphere, we could be in the regime where we have to integrate all of our data in order to get enough signal to noise. If we do that, we should be able to get down to a measurement of about 10 to the 11 molecules per square centimeter total column, which would really nail us down in terms of eliminating several possibilities for what might be producing a water vapor atmosphere. Also, in this particular cartoon, you can see the little illustration for where the LADI spacecraft orbit dipped down relatively nearest the surface, near the Dawn terminator. LADI, of course, found very, very little water vapor at that altitude, and mainly saw it changing with meteor storm impacts. We will know. Are we in the regime of the LADI background measurements of essentially nothing there or not? And if there are sudden big bursts of water vapor, because we intend to be measuring regularly throughout the day, we should be sensitive to that as well. This is an illustration of what kind of spectral line shape we expect depending on the abundance of water vapor above us. This particular one is for things that are on the high side of a surface-bounded exosphere, so an actual collisional atmosphere. And these are all measurements where we would be able to do that in principle within our first half second of operation. We will know that answer. It'll take us a few minutes to get the actual dividing line for a surface-bounded exosphere. If, on the other hand, we're on the other side and we're in a more minimalist atmosphere, we have to integrate longer, of course, but we can actually get down to very low abundances, still within measurement times on the order of minutes. Or if we have to combine data from, we should still be able over the course of a day to get an hour or two of total integration time, which will give us plenty of signal to noise to measure down to fairly small quantities, down to where we would estimate you might have an atmosphere that would be from the tension between delivery by solar wind or micrometeoroids or removal by solar wind phenomena and by photolysis. And with OH, we're really only expecting that we would be in the non-collisional regime. And again, because we could measure that to very high signal to noise in just a few minutes. That puts us back on the table, and that's it.
Okay, thanks, Tim. Do we have any questions? Tim, I think you mentioned this, but I may have blanked out while I was shoving salad in my mouth. How long is this surviving on the lunar surface? What's the length of it?
We have assumed that we would only have one single lunation mission during the daytime. Everything that we actually need to do, we should be able to do in about, well, we were targeting 12 days. It sounds like we probably won't get quite that close to dawn or dusk. But nevertheless, we ought to be able to finish everything in a one lunar day mission. Anything after that would be glorious, but not critically necessary.
So we've got a question from Jacob Richardson. Wants to know, how long might it take to measure the D/H ratio if possible?
We're really only going to be able to get that if we're in the regime where we have a tenuous collisional atmosphere. The reason why we can hold it on there is there's nothing descopable that would, if we were to descope the D/H ratio measurement, it doesn't save anything. It's actually the same spectrum that we use to measure water, because of the way we've designed the instrument, also measures the HDO transition. So if we are in the regime where we have 10 to the 15 molecules per square centimeter or more, at about 10 to the 16, the HDO line should be pretty measurable. And if that's true, then 10 minutes. I haven't memorized what it would require if we get down into the more tenuous regime.
Any other questions? All right. Thanks, Tim. I'm going to start a very slow